Okay, so we have been talking about functions, and the last two examples we spent a lot of time doing it were numerical functions. Okay, so number one, remember it was about optimization, and the other one in the maximize the enclosure when the amount of fencing material is fixed. The second one was motion, and I just want to, and we need to talk more about numbers. Questions? So we're going to talk more about numbers apart from functions, but to emphasize the difference, let me go back slightly to where we started, and the start was this, the set. So we started talking about sets, and the sets of, you remember that was the function, from the set of boys to the set of balls, and then we went on studying functions, but what is the difference between sets of arbitrary nature and the sets of numbers? So we actually try to, as you can see here, I try to number the boys and the balls, and so that we can makes our life slightly easier. But that's not what I'm talking about. What I'm talking about is the order that really is absolutely unimportant as far as the function like that is concerned. There is no first boy or first ball. It is exactly the same. So I could, okay, let me try again. I could rearrange the boy. I could arrange them in the order that has been indicated, but at the same time, I could choose another order. So as you can see, I put them. I want to put them in order. And one order is 1, 2, 3, 4 because that's the way they have been numbered. Come on, what is wrong with this thing? Like this, like that. Okay, and that's the order. Why do we care? Look at the pictures on the right. It is for visualization primarily. You visualize the function like that because you put these two sets in the form of put them on axes, and then the end result you have either table that's over there or the graph that is you barely see there on the right. So the order matters because we order them somehow, and it has to be ordered somehow. But there is no inherent order or direction among these two sets, among the members of the set. So I could take the same set and rearrange them, and the result would have to have absolutely the same. Would have to be absolutely the same. It makes absolutely no difference if I move these like this. And then the set is it's the same set. Remember, there is no structure to begin with, and the numbers don't match numbers anymore, and so there you go. There is really nothing else we can do. Then those graphs that we look at over there is really once we rearrange our set according to our whim, pretty much the graph will look different. Okay, so that's why in a way tables, if you are studying functions like this, as functions, tables are pretty much better because it is assumed that you can rearrange the rows and you can rearrange the columns, and it will be the same table, the same data, same function. Not so with numbers. If we actually talk about numbers, they have an inherent structure which is like here, and that structure several structures. Actually, number one structure is the order. Okay, so here we're talking about, remember what those two sets of numbers were. One was the time. It has the order. You progress in time from 1 minute to the next, to the next, to the next. On the other hand, the same with location. Those milestones are arranged in a particular order, and the numbers progress from 0 to 1 to 3 to 4. Okay, so which means that we do not have this luxury, for better or for worse. I'd say it's for better. We don't have this desire to rearrange numbers. So if numbers are as you can see here, 1, 2, 3, 4. Then that's the way then we keep them, and then there's only one way to put them accordingly in our table, which is on the right, as well as in the graph, which is on the left. So there's only one way to do it. So that's the good news. So ambiguity is gone, and that's what we start with when we study numbers. Study numbers is to look at the order. Okay, so numbers have order. Okay, so far, remember how we started with this problem. You can still see in this table over there that we start with the numbers that are integers. So this is we need to discuss. But number one is what kind of type of numbers we're dealing with first, and those are integers. So first, integers. So they are run from negative infinity to infinity, but we don't have to limit our don't have to so far face the infinity just yet. As you can see, you can study motion, and you don't really have to necessarily assume that there's a time goes to infinity in both directions, and the space goes to infinity in both directions. As long as these two sets are large enough, you're fine. Okay, so we assume that let's study our motion for 10 minutes. Okay, and that's fine. Or you can have 100 minutes. But so there's really no infinity to worry about. But it is certainly something to keep in mind, and we'll get to that later. Or maybe we'll have to wait until calculus. But that's the infinity that we have to just keep in mind, and I have a picture for you here. It's like think about like it's you approach a fence, and then it's made of those planks, and then you look to the left and to the right, and it seems to be going to forever, and you cannot see its end. If you cannot see its end, maybe it's infinite, maybe it's not. It's really, practically speaking, it doesn't matter. Okay, but you can, if you keep walking or try to walk in one direction or the other, you will discover more and more of that fence. But will it stop at some point? Maybe. It doesn't matter as far as we're concerned. So it is possible to actually assume that there is infinitely many planks, and that it is an infinitely long fence. But initially, it might not be as important. So that's one infinity that we have to keep in mind. There is the other infinity that I brought up last time, and that is not this one. What if we are zooming in? So you have your numbers, and you can zoom out, and you see like a fence, and you really zooming out, and you're looking at it more from a more larger distance. Then will it ever end? You zoom out, it might never end. Okay, but then you can try to zoom in too. So that's what we did last time, and that is what you see over there on the right. So if we're studying motion, and just for whatever reason, we are moving slow, then just looking at milestone is not enough. And so what happens is we introduced markings, half milestones, if you like, and you can literally see what that does. So if you start with this, and you might have no more than 10 milestones to begin with. So from 0 to 10, but then, like I said, if you want to capture your motion that is slower than 1 minute per mile, 1 minute per mile, or a mile per minute, then that's not enough. So initially, the picture that I showed you last time were these. This is your motion from initially 1 mile at a time, but then it's number one. But then number two, you might be moving half mile at a time, and then it means that your function being from time to space, does not give you intermediate values. There is no half mile on your list of possible locations. Okay, so what do you do? This is what you do. You just at will add more locations. So then like this. So you add. So this is what I'm talking about. Half miles like this. Okay, so you add half miles, and then if you're moving at a speed of half mile a minute, then everything is taken care of, and you can plot the graph. You have data and everything. That's what we did last time. Let me find it. It's not working. It's not working. Okay, so where is it? Not this. That's not it. Well, yeah, this. So here, as you can see, we have half mile at a time. If it is allowed to move a half mile per minute, then everything is taken care of. Okay, but that certainly never stops, as you realize that what if you move slower, quarter mile at a time, then what you do, you add more points, more and more markings, right? So I might then, so number 3, 1/4 mile per minute. So then our set of numbers representing locations once again is incomplete. So, but that's fine. It is our choice to create more markings on the road and like this. And there are more and more points, but once again, now you can move. You can represent that motion in that manner as a function, as a graph, fully. Okay, so if you look at the picture that I have created, you can certainly probably recognize what it looks like. What does it look like? You may have seen it before. What? A ruler, right? A ruler. I have a picture here somewhere. A ruler that might go. Here's my ruler. Here's a ruler. Okay. Typically you go inch, you go half inch, quarter inch, 1/8 of an inch, maybe even smaller, but at some point you stop. And just like with the other infinity, remember, is that fence infinite or not? Well, maybe not. We don't necessarily care that much. Same with the ruler. Do we stop or do we keep dividing into smaller and smaller pieces? And since we know we can do it, then we don't have to do it. We just every ruler stops at some point. So this is division by 2. Start with 1 inch, divide into half inch at a time, then quarter inch, 1/8 of an inch. But you might think about another example. If you can think of another example in everyday life, you can improve accuracy of your measurements or computations. So think decimal system. Decimal system and numbers. Say take your calculator, and in fact, in a calculator, you might, in fact, Excel does that too. You can have numbers here represented by as many digits as you want. So these are integers, right? But you can think of a situation when they are not, such as here, and so you could use. Let me do it here. You can have as many decimals as you like. So in this particular case, I could go with I could have my 1 decimal, okay, and then what happens if I add one more decimal? Then what does that mean? It means that I have inserted 10 more marks within each of the units. So, for example, if you are, well, that would be a metric system for you. So, for example, you have 1 meter, and you can divide it into 10 pieces. That is called a decimeter. Then you divide it in 1 more. You have centimeters. Divide 1 more. You have millimeters, and so on. So, and then you can have as many as you like. In fact, if you want to, you can have infinitely many. That doesn't matter. We know that we can do it, so just as well we can say we do it as many as necessary, and then just leave it. So we can have regular ruler, or you can have decimal ruler. So the difference will be only you divide not in half, but you divide in 10 equal parts. So that's the metric system for you. But the picture will look very similar. Okay. Okay, so like I said, these are the two infinities that we have to face. For the time being, we'll do fine without actually going to infinity, just knowing that we could go in that direction as far as we can and accommodate any possible need for numbers. Okay. So okay, so these are the numbers. Now we are moving on to visualizations. But first, let me mention some notation. And these are infinitely many. The integers, and there are infinitely many of them. So, like starting somewhere at, that's what dot 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 means. Start somewhere -5, -4, -3. Imagine that you started at some point, and then you go on in the middle. You reach these points, and then you keep going. Okay, so these are the integers denoted by capital Z. So in the book you'd see it written as like this. So it's just you know, boldface, right? So that's the, if it is printed, it's printed with a boldface, and if you do it on write it by hand, you write it in the way I did it on the right at the bottom. So there is a gap there, so you don't want to spend too much time doing this. So you just write, it's called the blackboard font. Okay. So anyway, so just notation for convenience, and then there are natural numbers. They start usually from 0, even though that varies. Some people like to start with 1. And it's well, the notation is capital N. So that's where we draw numbers from whenever we have a need for numbers. In fact, even though we divide our ruler into smaller and smaller pieces, and it appears that we start to deal with fractions, and indeed it is true. So 1/16th of an inch, for example, it is definitely a fraction, but you can also think of it as a unit of measurement. Okay, so which means that if you look at the ruler, it looks like integers. So this looks like Z. Okay, if you just choose your unit to be appropriate, the smallest possible unit is, I'm not sure if this is 1/16th of, this is actually 1/4 of a mile. Okay, so this 1/4 of a mile. So if you take 1/4 of a mile as a unit, then the markings on that road will look like a visualization of the integers. Okay, so how many quarter miles have I covered? Okay, and so the numbers will be these: 5, 4, 0, 1, 2, 3, 4, 5. Okay, if it is a ruler, then my unit is, I cannot tell for sure. I think it is 1/16th, right? This is 1/16th. The smallest marking is 1/16th of an inch. So then once again, if I look at this as a whole, then this is, if you got to ignore. So if you choose units, if you choose inches as units, then those numbers that you see will be the representation of the integers. Okay, but on the other hand, you can choose for your units to be 1/16th of an inch, and then your Z will be visible not with those numbers, but rather with the smallest markings. Okay, so if you don't continue on dividing into smaller and smaller pieces, you will end up with a representation of integers, just equally spaced markings on a straight line. Okay, so that's what Z looks like. Or if you look at N over here, it's just a smaller. It is, as we say, a subset, right? But otherwise, as you can see, Z looks like this, but it doesn't matter how close those markings are, it's still Z. So that's also Z. So if you are concerned about visualization, you can have as whatever units are. It doesn't matter. It will be still z. The advantage of this point of view is that it means that you will always, whenever we get to do algebra, all the algebra that you have to worry about is just integers. So no fractions to worry about, right? So if you do any kind of addition of 1/16 of an inch plus 3/16 of an inch, do you do fractions or do you do, what do you do? What? No, you could, you sure could, but think about 1/16 of an inch plus 2/16 of an inch. If you think of 1/16 of an inch as a unit, then you have 1 unit plus 2 units. You get what? You get 3 units, right? So you don't have to do fractions, you don't have to do decimals. As long as you are using the same units throughout, your algebra will remain the same as the algebra of integers. Okay, so whenever we get to algebra, shortly we'll talk more about that. At this time, the only thing that we care about is the order. So once again, the order is visible here, and you can start with z and then subdivide it further as we had to do when we studied motion. What remains there is the order. So there's which. There's a sequence of numbers, and they're progressed in an increasing manner from left to right. So usually we put an arrow over there to indicate in what direction the growth is going. So once again, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. It's once again, these are integers. 1, 2, 3, 4, 5. Okay, so just depending on the unit that you choose, they all produce the same exact algebra. Okay, so now we are moving towards visualization, and we're going to visualize numbers as on a straight line like this. So, well, in a way, we already have done that, but let's review this one more time. So here it is. Here. Go. Okay, so this is a visualization of what? Of the number line. The visualization of the number line. So it is literally, as what you see, is a straight line. Okay, a straight line. That's the construction start with. Step number 2, you indicate the direction, which I just mentioned. So direction, usually you draw it horizontally and point to the right, but it doesn't matter. Sometimes you are going to point it up. That's also good. The next step is identify the origin. That's where your 0 is going to be. Okay, and then you're going to need the unit. Okay, so that's number 4 that you have to specify in order to once again visualize numbers that might not be necessarily about things such as locations or time. Well, locations are definitely visualized by their nature. Time we cannot see, but at least we can imagine it. But you can simply count things. You count pencils or people, and those are numbers, and they once again should be visualized. And once again, this is how you would visualize them. So you add the unit, your choice, small, large. It's up to you. Okay, depending on the problem you're solving, and then finally, what you do is you repeat that unit many times to the left and to the right. That unit, just like measuring stick, measure, and then you align. Now you align your numbers, the integers, with the endpoints of those intervals. Okay, whether you go to infinity, you go directions or not, it is up to you. But this is how in 5 steps you have what we call the real line. Okay, this is the real line. So intervals and integers are spread evenly throughout that line. Okay, so think about either once again a measure, ruler, or milestones. You can, if you really want to visualize it, it doesn't matter. It is at this point in an abstract mathematical object, and we The only question remains is what is happening in between. So that is still to be concerned about. Between 0 and 1, is there any numbers between 0 and 1? And the answer is there might be if we want to. And once again, we can divide the way it is done on the ruler. And then there are numbers that have not been mentioned. If you divide and divide, there is still something. What number is missing between 0 and 1? 1/3. Between 0 and 1, you look at the ruler. Even though I have 1/16 of an inch available, but 1/3 of an inch is not. Okay, so that's just the way we divide. We have to be capable of dealing with any fractions at some point. But if the question is about visualization, we are okay. We know roughly where 1/3 is, and we just place it on our number line. Okay, so 1/3, whether or not there's a marking for it, we know roughly where it's supposed to be. So that's how we're gonna visualize that. There are beyond fractions. There are numbers such as square root of 2, which is not a fraction, and once again we will approximate it either decimally or not. And once again, we roughly know where to place it. It's here somewhere between 1 and 2, and once again we know how to visualize it. Okay. So, so that is how we visualize this set of numbers. If we include only the integers, that's one thing. Okay, and then there is also R, the real numbers. So, which means that it's the same markings, so the integers are still there. But in addition to those markings, we have also everything that is in between. So quite literally, so this is still 1, 2, 3, but as you can see, the whole thing is included, including, say, this is the point over here. Maybe square root of 2 is here somewhere, pi is here somewhere. Okay, so all of these numbers are also included. So just for the sake of visualization, we want to think of those intervals not made of those little markings, and only markings matter. You know, when you do your measurements, you will literally look at the nearest marking, right, and you write it down if you're doing some carpentry, right? So there is nothing beyond 1/16 of an inch if you're using that ruler. But mathematically, there might be things such as square root of 2 that is not one of the markings. In fact, 1/3 is not one of the markings. But square root of 2, where does square root of 2 come from? Historically or otherwise? Why we care about square root of 2?
It's in geometry or triangles.
Right. Exactly right. So, or either a square or a triangle. If you have a right triangle with two sides 1 and 1, the diagonal is square root of 2. So you have a room 10 by 10. How do you compute what is the length of the diagonal of that room? It will be square root of whatever 100 or 200. Okay, so all of these numbers that are not fractions, that are actually met they are encountered in real life daily. So we still need a place for them, and so we accommodate them, and then we think of these interval between 1 and 2 not as made of little dots, but rather it's made like this. So it's solid. Every little point between 0 and 1 is there. So there is no skipping. There are no cuts or anything like that. Okay. So let's talk about sets of numbers. So where do they come from? And it turns out they come from, well, that's one. The example, this is geometry naturally, but really you can just interpret it algebraically, right? How do I interpret that triangle in terms of algebra? It is the Pythagorean theorem, right? So if I take the Pythagorean theorem, then I have, according to the Pythagorean theorem, the square of one side plus the square of the other side is equal to the square of the third side, which might be unknown at this time, right? So 1, 1, and x. If I want to determine the diagonal of that square or the hypotenuse of that triangle, I end up with this equation. So 1 squared plus 1 squared is equal to x squared. Literally Pythagorean theorem written and in the algebraic sense. And now the question is this: find x. Okay, so we restate the geometric problem here. Find the hypotenuse of a triangle, or once again, let me make that picture. So it is in fact a square, 1 by 1. Okay, and we're looking at its diagonal. Okay, so a square room, and you want to know what is the diagonal distance if you go from one corner to the opposite. Now we turn into algebra, and that's where frequently numbers come from, including numbers that we have not seen before in this class, and that is numbers that are not integers and not even fractions. So square root of 2 is not a fraction. Okay, so the history goes way back to 500 BC, where they, at the time, the Pythagoreans thought that all numbers are fractions. They built the whole religion based on that, and then somebody discovered that square root of 2 is not a fraction. So that was a big blow to their religion. So they, as story goes, they forced him to commit suicide because, well, it cannot be. They could not reconcile the idea of their religious ideas with the mathematics that had this ironclad proof that square root of 2 cannot be a fraction. Okay, so that is a conflict that is very hard to handle. So then we cannot avoid numbers that are called irrational. So fractions, P over Q, are fractions, right? Remember that, fractions, where P and Q are integers, then that is a fraction, where PQ are integers. So you start forming fractions from integers, and they are called rational numbers. Why do we call them rational numbers? What? What? Infinite?
No.
Finite. Finite. No, I don't. No, it's the explanation is kind of silly. In fact, so there is no rationality here. It's just a different word for a fraction. What's another word for a fraction? What? No. No. Ratio. Right. So ratio. There you go. Ratio. Rational numbers. Okay, so these are rational numbers. Square root of 2 is not, just to be remembered, is not rational. And most numbers are not rational. Okay, and then where do those irrational numbers, so it's irrational. Where do those irrational numbers come from? Typically they come from equations. Just like the one that we have here. Okay, so if I take that equation again, and what do I have here? I have x squared is equal to 2. Okay, so that is the equation. So x satisfies this equation that comes from the Pythagorean theorem. Okay, and then you were supposed to solve it. Okay, so that's how I put this in a truly algebraic sense. You have an equation, just solve it. Okay, so we need to understand what it means to solve an equation, though. So what does it mean to solve an equation? What? Yes, but can you elaborate on that? Okay, find the number that it has not find the unspecified number. So find the number that is not specified, but has to satisfy the equation. Okay, so the number is x. It stands for that number that we don't know what it is, but we need to find such a number that would satisfy the equation. So forgetting all the algebraic tricks that we know how to solve it, in truth is, that's the question, that is the way it's posed to us, the way we would progress, we would just say, well, let's go trial and error. So I try x equals 0. What do I do to verify whether or not it is a solution? What do I do with it? Substitute. So 0 squared is equal to 2? No. So no. Okay, so no, 0 is not a solution. Okay, and then I keep going. I try x equal 1, substitute 1 squared is not equal to 2. Once again, no. I try x equal 2, and on and on and on. 2 squared is not equal to 2. So that way, it will take a while, but that doesn't matter. I mean, it's still to understand what it means to solve an equation, it is what's on the left. You try every number that we try, you should plug it in and see if it satisfies the equation. And if it does not, you discard it. If it does, then you put it in your pocket. Okay. So the rest is that's what it means to solve an equation. The rest of the methods that we develop to solve equations is means to an end. It's how, but what it means to solve an equation is crucial. And there's this very simple meaning. It is to find the number that satisfies the equation. There is always some kind of a issue, or some kind of a more or less practical problem behind every equation. So that's why we could put it in this kind of affirmative or rather, what's the word? It's like an order. Find that such a number. Why do we need to find it? Because, for example, we have a room which has a 1 by, or we have an object that it has 1 by 1 inch by inch, and we want to know its diagonal. Okay, so if I need to know the length of the diagonal, turns out I need to solve this equation. Okay, so behind every equation there is some kind of a problem that we're trying to solve. Okay, so and then the methods are to help us to solve those equations. Not really. They are not what it is about. The question is to understand what it means to solve an equation. So I try, after infinitely many tries, I try x equal to square root of x. Substitute square root of 2 squared is equal to 2. So yes, and I put it in the pocket. Okay, so and this is a tricky part. And we have to watch our grammar here. What should I watch? What should I watch for here? Well, once I found it, or let's put it this way, if I found that square root of 2 satisfies the equation, should I keep going? No? You sure? There might be more. Yeah. It could be. That's why the grammar has to be watched, because there might be more than one answer. In fact, there's the other one. What's the other one? Once again, infinitely many steps. Minus square root of 2. Right. You can confirm minus square root of 2 squared. Once is equal to 2 4, so it's once again yes. So after many tries, you try these two, and you end up with yet another solution. So it's not the solution, but a solution, right? And then we have to that is actually not good anymore. This is all not acceptable anymore, because if you read it, it says find a number that is not specified but satisfies the equation. It's not good enough anymore, because when we're trying to solve an equation, apart from the geometry that cannot have negative lengths. But if you were just facing that equation, x squared is equal to 2, the right way to put it is to solve an equation means find all values of x that, if substituted into the equation, give you the correct statement. The correct statement is what we were doing here. So if it is incorrect, then it's not a solution. If it is correct, then it is a solution. Okay. So once again, solving equation always includes finding all the solutions. So you cannot find one and be satisfied with it unless there is some kind of a setup of the problem that tells you that there is only one. It is satisfactory, such as if you're talking about the diagonal of like a square, then you need only one number. Obviously, you don't need the negative number. But generally speaking, you have to find all of them. And that's why all values means that there will be more than one. So I'm talking about, what am I talking about? More than one combined together. I'm talking about sets. So we're circling back to sets. No matter how simple your equation is, it might have many solutions. Combined together, they form a set. And as such and then that's what you're looking for. You need to find, so they combined together, they're called the solution set. So if you want to think of equation produces some definitive answer, equation producing one definitive answer, not square root of 2, negative square root of 2, it is 1 or the other taken together. It means that all of those solutions combined together form a solution set, and that is one and only answer. Okay, so in this particular case, x squared is equal to 2. The answer is the solution set is what? That's right. So I would put it carefully the way we did. How would I, what's the notation for this? Parentheses. Yeah. Like braces, like braces. So if your solution is a list of numbers, then we present sets as numbers in the form of you would just list them and then put the braces on it. So this is a typical example of how an equation is solved. Let me do one example that is crucial, and this is, well, let's do one more. X squared is equal to 1. The solution set is plus or minus 1. Okay, same way. Okay, how about this one? X squared is equal to negative 1. What? Well, but I need the answer. So the question is, the way to answer the question is on the right. So to solve an equation means to find all the values of x that satisfy the equation. So what's your answer? What have you found? Okay. What is the set? What?
Yeah.
No solution. Yes, but what is the set?
No.
No. Yeah, it is one of the words that it's called. The set is called, so the set that contains no elements. No, if you want to be careful, you ask to find the solution set, you have to specify what it is. See how nicely we did it over there. We specified the answer. This is a list, and it's totally unambiguous, and we don't even have to use any words here. So the answer is the empty set. That's the word that is used, the empty set. the null set, another term, null set, and this is the notation. Have you seen this notation before? All right, so that's the empty set. So when your equation has no solution, that's what what your answer might look like. It is a set, you see. So you still can say words. There is nothing wrong with using words. You know, notation is good, algebra is good, but you can just explain it with words, and you will get away with it 9 out of 10. So equations. Well, let me I have a couple of minutes left. A quadratic formula. Will always give you your solution set, but it varies. Quadratic formula, so ax squared plus bx plus c, remember this one, is equal to 0. Depends on a, b, and c. A is not equal to 0. And then the quadratic formula that x is equal to, so it gives you the answer right away, negative b plus or minus b squared minus 4ac over 2a. Now, how many? The only thing I want to answer is how many. How many solutions? You have a formula. How many solutions will you have? 2, maybe. Yeah?
The angular root, and if that number bigger than 0,
Yeah.
and this formula have 2 answers. If that one smaller than 0, it just have 1.
Right. So in fact, there are 3 cases. You can have 2 solutions when that root is the number inside the square root is positive. You will have, but if the number in the square root is 0, then you end up with plus or minus 0. What does that mean? It means that there's only one number. Okay? And then the third possibility, what's the third possibility? What if that number is negative? How many solutions? 0. Okay, so either you list these 2, or you list 1, or you say the empty set. Okay, so all right, the homework will be assigned later today.
Is the homework going to be due Friday?
Friday.